This is a lecture that was originally delivered by Ben King when he was a postdoc at Naturalis, and he gave it to the course Methods of Biodiversity Analysis. Ben has moved on to a different position, and the course has merged now with another course. Nevertheless, the lecture material is still very relevant and interesting. So here I'm trying to deliver what he presented, probably not as well, but let's do our best. So in this lecture, we are going to attempt to stick the landing on a whole bunch of different concepts. We have got introduced to phylogenies and how to interpret them, how to read them, how to reconstruct them. And also, for example, how to do that under the maximum likelihood criterion. That's going to play a role. We have also looked at phylogenetic comparative analyses, where we, with the same likelihood function, looked at state changes on a tree and looked for trait correlations, for example. So here then we have two different applications of phylogeny for the purpose of understanding biodiversity. The first one helps us, establish species and species boundaries and how taxonomies and so on using phylogenetic trees. And the other is to basically interrogate functional diversity, trait diversity, and how traits and characters change across the tree. Another thing that we already familiarized ourselves with is the use of phylogenetic tree to understand diversification processes on the tree, or at least to characterize them in terms of the main parameters that govern them. So that is really directly diversification. And here now comes the final piece of the puzzle, where we go and investigate whether maybe certain states and state changes have something to do with diversification rate changes. So let's try to set it up. To begin with, we have to talk a little bit about key innovations. So key innovations are a very important concept in evolutionary biology. The basic idea is that once in a while some new character state evolves, and it turns out that that character state is super duper useful. Now, the definition of what a key innovation is has changed a little through time. So, for example, it could just mean that something is super duper useful. But as the field progressed a little bit, the definition became refined to focus on an association with increased diversification rates. So there's a state change and then there's a rate change. That means that some things that are super duper useful are not, according to this definition, thought to be key innovations. And a good example of this is the size of the human brain. Our brains are supposedly useful, probably the key behind our dominance on the Earth, but it has not led to the evolution of very many different human species. So in that sense, it is not a key innovation because it has not promoted elevated diversification rates in us. Now, the concept makes sense, but it's kind of hard to all bring it together, because what you then have to show is that there is actually an association with state changes on the tree and diversification rate changes. And it would also be nice if you can explain why there is that rate change. So some kind of plausible underlying mechanism that caused the increased diversification, because otherwise maybe your state change, well, maybe that state change is just correlated with another character, and actually it's the other character that's really behind the increased diversification. Let's look real quick at a couple of types of key innovation. So here's one of them. Here we look at bats, and once upon a time, bats were just really aspirational mice on the ground, or maybe in trees, I don't know. But then they evolved flight, and well, that was good because well, a couple of reasons. Perhaps is some release of predation from predation, maybe some release from competition on the ground. And there's a lot of things to eat in the sky or high up in the trees. And as a result, there is actually very many species of bats. So probably the radiation and diversification of the bats has been promoted by their evolution of flight. So that first example was opening up a whole new world, kind of analogous to a new continent appearing or something like that. The second example is a little different. Here we are talking about an innovation that is just very useful in increasing fitness, and in this case it is the continuously growing incisors, which are good for the gnawing that rodents do. And in Dutch the word for rodents is knaagdieren, which means gnawing animals. So it's even in the name that they have these teeth that they can then nibble at things. Yet another type of key innovation is one that really in no way is good for the organism. Now, we looked a little bit at species boundaries and species concepts, and how committed we need to be to reproductive isolation. But surely reproductive isolation does play some role, even if we aren't married to the biological species concept and complete isolation. So, for example, there could be traits that simply make it easier to evolve a new reproductive barrier, such as some really obscure pollination mechanism, which makes it so that the pollinators are really dedicated to one type, and as soon as it's a little different, well, then they're probably not going to fly between those two types of flowers. So here, this is not really good for the orchids at all, but they have just structures that promote the evolution of reproductive isolation, and particularly what's called pre-zygotic isolation, right? So it just, the whole fertilization doesn't happen. So if such mechanisms exist, well, how can we detect them? One way, which is relatively straightforward, is to look at sister-clades. So here the general idea is that if, let's say, you have a giant phylogenetic tree, such as the tree of all the flowering plants, for example, then strewn across that tree there are all sorts of sister-clade pairs. And then you would be looking for sister-clades where one of the sisters has the state which you think promotes diversification, the other sister does not, and then it's a simple matter of looking at which clade is bigger of the two sisters. And what's kind of handy about that is that automatically these clades are going to be the same age. After all, they both descend from the same shared ancestor. So we then automatically get rid of the confounding variable where age matters, right? Like older clades perhaps are going to be bigger because they've had more time to accumulate lineages. That's not necessarily something we always see, but that all else being equal, that could be the case. So obviously these sister group techniques get rid of that because now these two sisters are the same age. So that's handy. Let's look at a quick example. Here we are looking at a phylogeny where somewhere on the tree arose what are called nectar spurs, which are perhaps a key innovation in flowering plants. And we can here see the shift towards having these spurs that takes place at the thick black bar with the number 6 next to it. So the top clade has the spurs, the others don't. Here they have them, this sister doesn't. Now then, if you were to go across the entire tree of flowering plants and you go and look for sisters where one sister is spurred and the other is non-spurred, then we come to find out that more often than not the spurred clade is bigger. We can see that in the third column from the left. We can see the ratio. For example, the first row there shows that the number of spurred species in Aquilegia is 70, and then semi-Aquilegia has only one species. So that is obviously kind of a notable difference in size. But we need more of them. So then in this table that's done a whole bunch of times, and more often than not the ratio skews towards greater species richness in the spurred clade. So here that is indeed the case. Groups with the trait are more diverse compared to their sister groups, and also more than expected by chance, because we see more often than not that case and only one exception. However, with this approach there are some problems. One of them is that we don't actually know, or at least we can't tell just by doing this, whether the pattern is caused by differences in speciation rate or extinction rate. For example, it could be that the evolution of the spurs is something that somehow protects against extinction, so the net diversification rate is elevated, but it doesn't actually promote speciation. Maybe it's even the case that the sister clade has higher extinction and that speciation does not evolve anywhere. Also, and this is maybe a bigger problem just in practical terms, you throw away a lot of information. Like you need, for every data point, you need 2 whole clades next to each other. And so, they need to meet a whole bunch of different criteria. They would have to be monophyletic with respect to the state change. And they need to be not nested or anything. They need to be side by side. And, how often do you find that on a tree? Maybe on a huge tree like the flowering plants, yes. But in general, it is not particularly efficient with our data. As you can see here, so everything here within the oval is just simply thrown away in this study. Here's another problem which is a bit more subtle, but it also plays a role. So here we are looking at a simulated tree. And here in this tree simulation, so the tree is kind of grown from the roots to the tips, basically by playing sort of lotteries where we allow clades or lineages to speciate at some rate. And in this case we actually have 2 rates, because we have one rate for when you are in the state of the black circle. So somewhere on the branch when you're the black circle, you are a quick speciator. And if you have the state of the white circle, then you are a slow speciator. And then the result that this produces is a tree where most of the tips are black, because those lineages were speciating quickly. However, the same effect can also be accomplished if the transition rates between the states is asymmetrical. So here we are basically looking at the visualization of a simple Q matrix. So let's think back to our likelihood substitution or transition models. In this case, we have a two-state character, so the Q matrix is very small. We have a forward rate and a reverse rate, and they are different. So here we are very quickly going from white circle, the state of white circle, to becoming the state of black circle. But the opposite direction happens more rarely, has a lower rate. And that also results in a tree with very many black tips and fewer white tips. So actually nothing to do with speciation rate, but just with asymmetry in the transition rates. So those are all problems because this is all kind of, confounded. And so we need to introduce some other methods that allow us to disentangle that. So let's get busy with BISSE. So the binary state speciation and extinction method avoids the effects that we just discussed, where character state changes and the rates between those states are confounded with diversification rates. So here with BISSE we can disentangle that. This is a likelihood method which is based on an explicit model of evolution. And here now a whole bunch of things are starting to come together. We see again a little Q matrix where we have the rate for going from 0 to 1, so that's Q01. We have the rate of going from 1 to 0, Q10. So those are the two transition rates from the Q matrix. We also have our parameters for speciation and extinction, respectively lambda and mu. And now we have two rate classes for each of them because they have become conditional on the state that they were in. So if you are a lineage traveling through time and you occupy state 1, so you are a black circle organism, well, then your speciation rate is lambda 1. And your extinction rate is mu1, and if you go extinct, well, then you leave the game, hence the arrow pointing out. Likewise, for state 0, there is lambda 0 speciation rate and extinction rate mu0. So we have two states, 0 and 1, and we have for each state a speciation parameter value, respectively lambda 0, lambda 1, and extinction parameter mu0, mu1. And we transition between states. So then what does BISSE do with this? Well, BISSE uses the pruning algorithm of Joe Felsenstein. I talked earlier on about how Joe Felsenstein has invented everything in phylogenetics, such as, for example, independent contrasts back when we were doing comparative methods. He also invented this, just to get a quick intuition for what's going on here. You recall that for calculating the likelihood, you have to consider all permutations of all states that all nodes can occupy. So that is a whole lot of different combinations. And you can do that brute force and inefficiently. You can also be a little bit clever, like Joe Felsenstein, and do what you might call a dynamic programming approach, where basically you start with your calculations near the tips, and then you basically carry over your intermediate results as you traverse towards the root. So that is why here too on these figures we are moving from the tips to the root. So the explored territory is marked black, and then the as yet unexplored territory is gray. Then what do we see on panel A on the left? Well, we travel a tiny little bit along the branch between time t and then time t plus delta t. And during that infinitesimally small increment, there is no state change and no speciation, so nothing happens. Or, for example, in panel B, we again traverse this same kind of little stretch of branch, and there is a state change. So now we've gone from state 1 to state 0. Or on panel C, there is no state change, so it's still state 0, but there is a speciation event, which the method hypothesizes basically, and then that branch goes extinct again. Or the same along panel D, on panel D, but then just mirrored, basically. So it has to do this, like a great deal of combinatorics, traveling from the tips to the root, and it, in doing so, explores a whole range of parameter values. And including those values that maximize the likelihood. So here what we are looking for is to obtain maximum likelihood estimates of our parameter values. However, as we have heard before, sometimes these heuristic searches can be inefficient and can maybe not find the true maximum likelihood estimate. So this is kind of analogous to how there is these bumpy optimality landscapes that lead us to, for example, use the parsimony ratchet at the maximum parsimony, and that maybe also make it a good idea to do things such as Bayesian methods with Markov chain Monte Carlo, so that we have kind of a greater exploration of the whole landscape, and that then is reflected in our measures of uncertainty. Anyway, so that has a little bit also to do with local optima, and here too, this is something that can be encountered. So then what exactly is the application? Well, for BISSE, the application is in model testing. So we have a model with a whole bunch of different parameters, and what we are going to do is to compare basically different models, maybe simpler ones and more complex ones, and see how well they fit the data. So here, for example, we have two competing models. On the left we have basically a null model, where we say, well, you know, diversification rate is independent of the state that you're in. So, for example, for speciation, whether you're in state 0 or state 1, your rate is baby blue. And for extinction, likewise, no matter if you're in state 0 or state 1, your extinction rate is old pink, I guess. And then compare and contrast this with the model on the right, which is a model of trait-dependent diversification, where the speciation rate depends on what state you are in. So if your lineage is in state 0, the speciation rate is baby blue, and if you're in a state 1, it is more like Prussian blue. Whereas for the extinction rate, in state 0 it's again old pink, and then in state 1 it's, I don't know, burgundy. So, this is obviously a slightly more complex model. For each of these, we then calculate the likelihood. So then here comes the testing, and just to set this up a little bit, with model testing, we have a kind of Goldilocks situation where, you can have an overly simplistic model, such as the one shown on the left, where we've fitted some kind of linear regression that goes through the point cloud, but clearly there's a bit more going on than just a linear relationship. And maybe, for example, the one in the middle is better. I don't know, maybe this is some kind of, I don't know what curve is being fitted here, but it fits at least better than the linear one. Then the one on the right, okay, the line goes very politely through basically every data point, but that seems a bit zigzaggy. Maybe there's also just a little bit of error in our data points. So now we're just really overfitting, and maybe that's something to avoid. Two ways to avoid that are the Adequacy information criterion, or AIC, and likelihood ratio tests, and they're really quite similar. So with the AIC, we obtain for each model the AIC value, which consists of the log likelihood times 2, which we subtract from the number of parameters in our model times 2. So here, this term that's now indicated is basically the raw model fit, but then this other term is a penalty for the number of parameters. So, as we start fitting better and better because we add more and more parameters, well, at some point that has diminishing results, because then we are overfitting, and with this penalty we kind of stop adding parameters because they become relatively more and more costly. So then how does that pan out when we do our model testing? Here again we have our null model of independence, and we have our trait dependent model. And then, for example, one of them might have a log likelihood of 680.6 for the null, and the other one has a log likelihood of 680.5, which is better. So with these log likelihoods, they are negative numbers, and then this is, closer to 0, so better. Well, but how much better? Not enough. This is not enough. We cannot reject the null. Well, maybe here in a different scenario, we have our null model with a value like this, and then we have our other model with more parameters, and it has a better likelihood, and in this case, it is actually significantly better. So we weren't overfitting. We were actually on the right track here. Okay, nevertheless, the BISSE method has its limitations. So one of them is the limitation which we kind of alluded to earlier, that maybe we are just looking at the wrong character, right? Maybe that character is correlated with another character, and that other character actually is the one that promotes diversification rate shifts. Although maybe this is less likely if there are multiple origins of the character. So the state shift happens in a bunch of different places strewn across the tree. Now, an example of the first problem is this one. So here, Detritia is a very, very species-rich group of butterflies. Now, why are they so species-rich? There's actually a bunch of different synapomorphies, so shared derived characters, that define this whole group. For example, how the egg-laying tract is organized, but also how the renal system is organized. So if they both shift along the same branch, well, how would you know which one it is? So this kind of also relates to this problem of phylogenetic pseudoreplication, which we also saw in the introduction to comparative analyses. So what are we looking at here? We are looking at 4 panels, and each panel there's 2 trees that mirror each other, so the tips are facing. And then on each of the 2 versions of the tree, a different character is plotted. So for example, on panel C, we see that there's character X and character Y, and X shifts once, Y shifts once, both from white to black. And then when we just look at the tips, well, there's a whole bunch of tips that are correlated, but they all stem from the same single state shift. So that's pseudo-replication. The same is true for panel D. Here we see that, okay, the shifts are a little different for Y in that it arises multiple times, but all within the clade that has a single shift for X. So that's now good. What we need is what's shown in panels A and B, where in multiple independent locations both traits arise. And BISSE is a little sensitive to this, just like other methods of character analysis are also. So here's another one, and we are kind of wondering if this, what is precisely going on here, whether this is a false positive and how it works. So just to set it up, here we're looking at marine mammals, including dolphins, and there's big ones and small ones. So if we ran this through BISSE, we see that the small body size appears to promote diversification in the dolphins. However, we can also simulate neutral characters on the tree. So here, the column that is now indicated with the word simulation, those were just evolved on the tree, but not having to do with speciation at all. And lo and behold, they also paint the dolphin clade more or less entirely white. So if we were to run BISSE on that simulated trait, then it turns out that in very many attempts we recover a positive association between state changes and rate changes, essentially. And this is, again, especially a risk when there's very few state changes, independent state changes on the tree. But even if there are many transitions, such false positives are still sometimes produced by BISSE. Here there's many state changes, and here it might happen too. So what exactly is going on here? It's not quite a type 1 error, because that is an error when the null model is correct, yet we choose the alternative. Here that's not what's going on. So here our null model is one of constant diversification. Remember, here's the model. So irrespective of what state we are in, the speciation rate is the same, baby blue, and the extinction rate is the same, old pink. But BISSE is actually constraining the solutions that are possible here, because it only allows the diversification rate regimes to differ in a way that exactly coincides with the states. And maybe that doesn't always happen. So in that case, our model is inadequate. So for example, a thing that might be going on is that on our tree there is indeed different diversification rates. So different rate classes are necessary in order to optimize on the tree. But those different regimes have nothing to do with the state changes, except this is the only option that the algorithm has. So it kind of comes up with an association between the two where none exists. So maybe the real model is actually that there needs to be these multiple regimes within the same state. So now here we have within state 0 two rates, and within state 1 two rates, both for speciation and extinction. We can interrogate that a bit more adequately using what are called hidden states. So here again we have our states 0 and 1, but within those states there could be a whole spectrum potentially of rates, or maybe multiple rate classes, like class A, B, and C in state 0 and A, B, and C in state 1, which are kind of hidden from the onset, on the outset, but that would accommodate multiple diversification rates spread out across our tree. So then how does that work? Basically the box plots on the left illustrate this. We have within state 0 kind of a spread in the net diversification rate, and also within state 1. Let's just look at an example. So here we are looking at a close-up of strawberry. And as you know, in strawberries, the little seeds are on the outside, and that's called an achene fruit. And now the question is, well, is that actually a character that promotes diversification? So let's check it out. Here we have the tree, and BISSE says, well, it looks like there's an association. So how do we read this tree? In this radial tree, the branches are painted with the character states, such that those branches that are white have that fruit on the outside, and the branches that are black don't. Then BISSE shows how it has then applied different rate classes by coloring the outlines of the branches. So then the kind of fuchsia outline is a high diversification rate, and the kind of purple is a low diversification rate. And it looks like this coincides just beautifully. However, if we throw a hissy fit, we see that, obviously the branches are still white and black in the according to the same pattern, because, well, the states at the tip are still the same. But then the different rate classes, of which there's now a whole spectrum, show a considerable amount of variation within each of these clades. So the clades with the white branches are both outlined in red here and there, and in purple here and there. And actually kind of the same is true for the black branches that are sometimes red and sometimes purple as well. So what we were initially doing is wrong. We were shoehorning it in such a way that the algorithm had to conclude that rates and states are associated, just because it had no way around that, basically. So these hidden states models can also be used to construct more appropriate null models. So the naive null model that we were working on so far is one where there's just a single speciation rate and a single extinction rate across the entire tree, whereas the BISSE model had multiple rates. So the real thing that we want to be doing is to allow as a null also for there to be multiple rate classes. So a better comparison would be to a model that contains the same amount of diversification rate heterogeneity, so light blue, dark blue, for example, but not linked to the traits, thusly. So here you can see that we still have state 0, state 1, but within state 0 there is rate A and rate B, and likewise within state 1 there's rate A and rate B. And that's it. Thank you very much. I think we've explored a lot and learned about trait-dependent diversification. So here we've attempted to really stick the landing in terms of the methods to bring together how traits can promote the evolution of large clades. Thank you very much.